A car's position is given by the function s of t equals 5t squared plus 2t, where the s is measured in meters and t is measured in seconds. What does the derivative s prime of t represent in this concept? Well, this is a particle or a position type problem, okay? Rectilinear motion, it's called. And whenever you're given the position function, its derivative is going to be the velocity at a given time. So this is basically just a introduction to Unit 4, where we are simply asking you, hey, what does the derivative of a position function give you? Velocity. If you're curious, the second derivative would give you acceleration, but I didn't ask you that, now did I? So thanks for watching. Like and subscribe. The temperature T in degrees Celsius of a cup of coffee over time T in minutes is modeled by the function T of T, oh boy, that's not confusing at all, equals 100, blah, 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 blah. What does T prime of 5 represent? All right, so you have temperature with respect to time. When you take the derivative, you are given a rate. Okay, so your T and your T is going to be temperature, the rate of the temperature over that many minutes time 5 minutes. Okay, so it's the rate of change of the temperature of the coffee after 5 minutes. So yeah, maybe I could have done a better job describing that, but when you take the derivative of something, you find the rate. Okay. And since we have, usually rates are like miles per hour, but this is going to be temperature over minutes, right? And when you use 5, you are plugging in 5 into little t, so you're talking about 5 minutes, so the rate of change of the temperature of the coffee after 5 minutes. So there you go. Explained it poorly the first time, explained it slightly better the second time. You're welcome. Thanks for watching. The home price index as a percentage change from the year 2003 in year t is represented by y equals p of t. So we're given y equals p of t, this weird function where the home price index, whatever that means, goes up and then peaks out and then goes down and levels out and blah, blah, blah. All right. What year does p prime of t equal 0? Well, p prime is the derivative. The derivative means slope. So when it's asking you when is the slope equal to 0, it's asking you when is the slope completely flat and horizontal. Okay, so I'm looking at this and I'm pretending slope is kind of like if I were to be on this thing riding a skateboard, where would my skateboard be completely flat? Well, always at the top of a hill or at the bottom of a valley is where it's going to be completely flat. Okay, I'm going up, going up, going up, going up, going up, and the minute that I hit the tippy top here, I am flat. That is the year 2006. So the year that my derivative is 0 is asking when is the year that my instantaneous slope, my instantaneous rate of change is horizontal, and that happens at the year 2006. Similar question, is p prime, so again, the slope, of 2008 positive, negative, or 0? So I'm going to this, I'm pretending I'm on my skateboard, and at 2008, right, I am going down this hill. So at that moment at 2008, I have a negative slope because my slope is going down and to the right. Now C is asking us to find the average rate of change from 2006 to 2008. So I'm going to look at those 2 points right there, 2006 and 2008. 2006 is right there. That's the point 2006, 40. 2008 is right there. That's the point 2008, 25. Now what I'm going to do is I'm going to use the average rate of change formula, which is f of b minus f of a over b minus a. Okay, let me change my pen. There we go. We'll call the earlier year A because that usually makes sense. So you would be f of A. We'll call the later year B, so you'll be f of B, like so. And it's just a matter of plugging things in. F of B is 25, minus f of A is 40. Regular B is 2008. Regular A is 2006. 25 minus 40 is negative 15. 2008 minus 2006 is 2, and we could basically just call that negative 15 over 2. Unless you want to call it negative 7.5, that's perfectly fine. Now, why does this make sense? Well, going back over here, if I were to find the average rate of change, that's them asking you to find the slope between 2 points. So my slope would look something like this if I knew how to draw a straight line. And if I were normally, like back in Algebra 1, being asked to find the slope of a line, you would just take those 2 points and say, oh, okay, well, every time I go down 5. So down 5, 10, 15. And every time I go over 1. So over 2. Down 15 over 2, negative 15 over 2. Easy peasy. So yeah, that's how you do that problem. Lots of derivative stuff, but also lots of fun. The number of iPods sold by Apple each year from 2004 through 2007 can be approximated by this formula right here. It's a quadratic in millions of iPods where t equals 0 represents 2004. Lots going on here. So I know that this is a parabola, and when graphed it's going to look like this. What I don't know is where things change, and that's going to help me understand A and B. All right. A is asking where it's increasing or decreasing. Well, I don't know where it's increasing. I don't know where the vertex is. I could find it, but I'm going to use calculus to do it instead. If I want to know if it's increasing or decreasing, I can just find the slope and see if the slope is negative or positive. Now, how do I use calculus to find the slope? Take the derivative. F prime of t is going to give us the slope, okay, at any given t. So when I take the derivative, this is just power rule, the derivative of negative t squared is negative 2t. The derivative of 20t is plus 20, and then plus 3 does nothing for me. Now I care about 2006. Does that mean I plug in 2006? No, 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 no. 0 is 2004. So 2006 implies that t is going to equal 0 because t equals 2 because it's 2 years later. So I'm going to find f prime of 2. F prime of 2 is going to be negative 2 times positive 2 plus 20. Negative 2 times 2 is negative 4, and negative 4 plus 20 is positive 16. The key word there being positive. And what this means is since I have a positive slope, remember derivative gives us slope, since I have a positive slope, that means it is increasing at that number right there. So the answer to problem A is increasing. Okay? Fun stuff. Now B is saying, what is the average rate of change from 2004 to 2007? So I'm going to use the average rate of change formula, which is f of B minus f of A over B minus A. The frustrating thing here is I don't have any information except for the fact that I can find out what my years are. All right? 2004 is the year 0. Which means 2007 is going to be 3 years later, the year 3. Now, do I have my y values? Do I have my f of a and f of b? No, I don't. So you would be my a, you would be my b. In order to find f of a, what I'm going to do is find f of 0 by plugging it into the original function. So negative 0 in parentheses squared plus 20 times 0 plus 3 is going to be 0, 0, and 3. You get 3. So f of a is going to be 3. F of b is going to be me plugging in 3, so f of 3, and that is going to equal negative 3 squared, again I'm plugging it into the original function, plus 20 times 3 plus 3, which is going to be 9 plus, I'm sorry, that was a close one, negative 9, plus 60, so 51, plus 3, 54. And that's f of b. So let's plug it all in. Let's plug and chug. All right, f of b minus f of a is going to be 54 minus 3. b minus a is going to be 3 minus 0. Okay, 51 over 3, I'm pretty sure is 17. So the average rate of change is going to be 17 million. Now, where did I get that million from? I don't think Apple only sold 17 iPods per year. They probably sold a few more than that. I don't know. I don't know business, but it says up here that it's in million. So the average rate of change is going to be 17. Between 2004 and 2007, they sold 17 million iPods or iPads or whatevers per year. And yeah, that's how you do it. Fun stuff. The graph of the differentiable function y equals f of x is shown below. Which of the following is true? So we've got this parabola-looking guy. It's decreasing there, it's increasing there. We have a bottom there. So knowing calculus, we're probably going to talk about the fact that the derivative, and we'll say this, let's use words. The derivative, right, is going to be negative. Since it's decreasing, that means the derivative, which is slope, the derivative is going to be negative on the interval negative infinity to 1, but not including 1. It's going to be 0 at 1, and it's going to be positive from 1 on to positive infinity. All right, now, whether that's exactly what we're looking at, I don't know. I'm supposed to find out which of the following is true. So, the derivative at 0 looks like to be negative 1-ish, right? So like that, the derivative at 0 is like negative 1-ish, and that's going to be greater than when you plug in 0. Okay, well, let's look at each part. Okay, the derivative at 0 is negative. When you plug in 0, you get 0. Is negative bigger than 0? No, A is not true. All right, so let's get rid of that. B is saying the derivative at 1 is 0, and when you plug in 1, you get negative 1. Is 0 less than negative 1? No. So you're not true. F prime of 2 is going to be some positive slope, right? And f of 2 is 0. Is a positive number less than 0? No. So far we're striking out big time. Striking out big time. F prime of 1 is going to be the derivative at 1, which is 0. 0 is equal to f of 0, which is true. F of 0 is 0, and the derivative at 1 is also 0. D is true. Now, I'm assuming we're maybe just finding 1. Maybe this is one of those select all that apply. I could be wrong. Let's just keep going. F prime of 2 is going to be some positive number we don't know. F of 2 is going to be 0. Is a positive number bigger than 0? No. So this is one of those only one answer things, and the only one answer that seemed to work is D, baby. A car's position s of t in meters is modeled by the function s of t equals 3t squared plus 2t plus 5, where t is time in seconds. Find the velocity, find the acceleration. If you're given s of t, and that's the position function, which is what we're given here, okay, this is from the section called rectilinear motion. Okay, what you do is if you take the derivative gives you the velocity at a specific time whenever you plug in t. The second derivative is going to give you acceleration at that specific time. I don't even know how to spell acceleration, so look at that. I'm going to cheat. So A is asking me to find the velocity at t equals 4. That requires me to find the derivative of s. So the velocity function s prime of t is going to use the power rule. The derivative of 3t squared is 6t. The derivative of 2t is 2, and the derivative of 5 is nothing. Okay, at 4, we say s prime of 4 is going to equal 6, replace t with 4, plus 2. Okay, 24 plus 2 is 26. Now, since we have time in seconds and we have meters, our rate is going to be 26 meters per second. Okay, and so that's going to be the rate, meters per second. Now, the second derivative is going to give us our acceleration at time t. So s double prime of t is going to be the derivative of s single prime of t. The derivative of 6t is 6. The derivative of 2 is nothing. So when I quote-unquote plug in 4, quote-unquote, there's no t to plug it into, and I still get 6. So this is not 6 meters per second. This is 6 meters per second, or per second squared, because you took the derivative again. Okay, so you do that. Is basically, you know how you have, d squared y, d dx squared. Same idea. You are taking the d dx squared of everything by taking the second derivative. So these are my guys, and yeah, that's how you find velocity and acceleration. A particle moves along a line so that its position at any time t, as long as it's a positive t, because you can't go back in time, is given by this wacky function right here, where s is measured in meters and t is measured in seconds. If you are given a position function, okay, this is called rectilinear motion. If you are given a that's positive. Nope, I can keep going. Position, I nailed it. The first derivative gives you velocity. The second derivative gives you acceleration. So the first problem is find the instantaneous velocity at any time t. That's just asking what the first derivative is. Okay, so s prime of t is going to be using the power rule and taking the derivative of each and every term up here. The derivative of negative t cubed is negative 3t squared. The derivative of 7t squared is 14t. The derivative of negative 16t is negative 16, and the derivative of 8 is nothing. So that is my instantaneous velocity function at any time t. Nothing to plug in, we're done. B is asking us to find the acceleration at any time t. Similar idea, we're going to take the second derivative, which is the derivative of the first derivative. So we're going to use the power rule a couple times again. The derivative of negative 3t squared is going to be negative 6t. The derivative of 14t is 14, and the derivative of negative 16 is nothing. So that's my acceleration function at any time t. Now, using common sense, the particle is at rest means it's not moving. Okay, so the particle is at rest when your velocity is 0. So let's go back to our velocity function and see what happens when the velocity is 0. Okay, so I'm going to, this is going to be awful. I'm going to set this guy equal to 0 and rip out a negative. So I have 3t squared minus 14t plus 16, and see if I can factor that guy out. Let me see. One of them's got to be 3t minus 8 minus 2. 3t squared minus 6t minus, yeah, that'll work. Oh, how about that? Okay, so that equals 0. Okay. What I need to do is I have two factors here. Okay, the obvious factor is going to be t equals 0, so that's good news. The other one I'm going to set equal to 0 and solve, so 3t minus 8 equals 0 has me adding 8 to both sides, 3t equals 8, divide by 3, t equals 8 over 3. Okay, so one of the things I actually have to really be careful of is if I were to get a negative one of these, that's not possible because t can't be negative. Both of these were positive, so that makes me happy. So the times that these are at rest are actually realistic, legitimate times. And that happens at 2 seconds and 8/3 of a second. Okay, there you have it. Now, displacement of the particle for the first 3 seconds, what does that mean? Well, that just means where is your guy after 3 seconds? Where does it travel? The way you do that is if you were to have like an interval, in our case, interval is from 0 to 3. If I label you A and B, I am finding S of B minus S of A. In other words, where am I at 3 seconds? Where am I at 0 seconds? Subtract the one from the other. Okay, so let's find out what S of B, which is S of 3, is. S of 3 is going to be negative 3 cubed plus 7, 3 squared minus 16, 3 plus 8. So that's going to be 27. Let's attach a negative to it. 9 times, so that's 9 times 7, which is going to be plus 63 minus 48 plus 8 is going to equal negative 4. So this particle is like 4 feet underground, whatever that means. S of, did I do? Okay, so no, that's not where it starts, though. That's where it ends up. Ooh, close one. S of 0 is going to be much friendlier. S of 0 is going to be 0 plus 0 plus 0 plus 8, which is 8. So I start 8 feet in the air, whatever that means. I end 4 feet underground, which means my total displacement where I am now, or where I started at the beginning to where I am now, is going to be a distance of 12 meters traveled. Ooh. So yeah, lots going on here, but yeah, we did it. I had fun doing it too. I hope you did. A particle moves along the x-axis so that at time t, its position is given by x of t equals t cubed minus 6t squared plus 9t plus 11, where t is measured in seconds and x is measured in feet. All right, so you have this guy moving along the x-axis, okay? Now, this is its position. This is where it is on the x-axis left to right. Which means, looking at this problem, we were talking about velocity. We're talking about maybe acceleration. But let's at least, I see the word velocity. Let's try to understand what velocity means in this context, because I see that phrase right there. Okay, the derivative is velocity. Now, a negative velocity is real. I mean, I know in the real world, if I were to, drive backwards 10 miles an hour, I wouldn't say that, oh, I'm going negative 10 miles an hour, but that's actually what we're doing. All right, so here, a negative velocity would mean going left. So if this is negative, that would mean we're going left. If this is positive, that would mean we're going right. So what I want to do with this first guy is at t equals 0, is the particle moving right or left? I need to take the derivative, okay, and see where I'm at when t equals 0. So that's going to be x prime of t equals, power rule a bunch of times, 3t squared minus 12t plus 9. Okay. This is very simple because I'm plugging in 0. So x prime of 0 is going to be 0 minus 0 plus 9, right? And that's going to be a positive 9. So a positive 9 means at this moment I am going positive 9 feet per second. So since it's positive, that indicates that I'm going right. So I'm going right because I have a positive velocity at t equals 0. So that's me explaining without having to explain too much because I don't feel like it. At t equals 1 is the velocity of the particle increasing or decreasing. Now this is very, very, very similar to what we just did, because if I were to take the derivative again, that would give us acceleration. Now acceleration is you speeding up or slowing down. Okay, so if I were to, at a specific point, and at this point 1, if I were to get something that's negative, that means at the moment I'm slowing down. Okay, if I were to get something positive, that means I'm speeding up at that moment, right? I know those words aren't being used here. And this is asking if the velocity is increasing or decreasing. That's the same thing. If I'm driving, right, and my miles per hour goes from 10 to 12 to 14, that's me accelerating. So this is the same idea. So what I need to do is I need to take the derivative of u, so it's going to be power rule again a couple times, and then plug in 1 and see what happens. So if I take the derivative of x prime of t, that gets me the second derivative. Power rule is going to give me 3t squared becomes 6 regular t Minus 12t becomes minus 12, and then plus 9 disappears. I care about what happens at t equals 1. So x double prime of 1 is going to be 6 times 1 minus 12, which is 6 minus 12, which is negative 6. So that negative 6 indicates that I'm slowing down. So my velocity is decreasing because I have a negative acceleration. Okay? And that would be why. So what else? Find all values of t for the particle that's moving left. All right, so again, this goes back to the moving left problem. This goes back to problem A. So problem A, what I have is I care about when it's moving left, and that's going to involve me finding out all the intervals where I have a negative velocity. So let's take this guy. Okay, now when you have a particle moving left or right, you care about the negative velocity, which means we care about when velocity changes. So what I have to do is find out when the velocity is completely zero, and that'll indicate where my velocity changes. So what I do is I set u equal to 0, and I'm going to factor that equation out. First thing I can do is I can pull out a 3. That's going to make life easier. T squared minus 4t plus 3. And that's going to allow me to factor out to 0 equals 3, t minus 1, t minus 3, which means my magic numbers are going to be 1 and 3. 1 and 3 are my critical points, which means 1 and 3 is where the velocity is 0. That means I'm stopped at that moment. So I'm expecting this guy to move from like right to left to right. But how do I know that? Well, let's make ourselves a sign table for x prime of t, right, of t, and my zeros are 1 and 3. I know it's moving left if at any moment I plug in a number into the derivative and get a negative number. I know it's moving right if I plug in any point into the derivative and get a positive number. So what I'm going to do is I'm going to pick negative, 100, and in my mind plug it in. Actually, you know what? No. I already did that. I'm just going to plug in 0 because I wasn't thinking there. So I'm going to plug in 0. I'll plug in 2, and I'll plug in positive 100 to see what I get. I know from part A that when I plug in 0 into the derivative, I got a positive velocity. So you are positive up here. So you're not moving left, you're moving right. If I plug in 2 into the derivative, I would get 3 times 4, which is 12, minus 24 plus 9, which is a negative number. If I were to plug in 100, I would get 3 times like a really huge number minus like 1200 plus 9. That's going to stay positive. Okay, so that's my sign table. According to my sign table, I am negative between 1 and 3, which means I'm moving left between 1 and 3. So the values of t, where this particle is moving left, is going to be t is in between 1 and 3. Including 1 and 3? No, because at 1, you're stopped. And at 3, you're stopped. So this is me writing it out in inequality notation. You could use the parentheses 1 comma parentheses 3. Whatever works. In between 1 second and 3 seconds is when we are, seconds, right? Yes, seconds is when we are moving to the left. Okay, so that is C. Last but not least, we got displacement. Displacement is where you are now at the moment, not how your distance traveled. Where are you, according to Blink-182? Get it? Miss You? It's a lyric in Miss You. I also said to the left. It made me think of Cupid Shuffle, but I didn't sing that. How do I find displacement? Well, my original position function is x of t. So my displacement is found by taking where you are now, 6 seconds, and subtracting where you were at the beginning. So I need to find x of 6, and I need to find x of 0. So x of 6 is going to be 6 cubed minus 6 times 6 squared plus 9 times 6 plus 11. This is actually super convenient because 6 cubed minus 6 times 6 squared is also 6 cubed, so you completely go away. And you become 54 plus 11, which is 65. x of 0 is going to be 0, 0, 0, 0, 0, 0, 11. So my displacement is going to be, I'm now at 65 feet to the right. I'm subtracting 11 feet to the right, which means I went from 11 to 55, and that is a change of, why am I struggling, 54 feet? So there you have it, 54 feet. So very involved problem, but we covered a lot of things here in this problem. I enjoyed it. It was fun. If the position of an ant traveling along a horizontal path at time t is 3t squared plus 1, what is the ant's average velocity from t equals 1 to t equals 6? I know what you're thinking. Take the derivative. Nope, 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 nope. Average velocity means average rate of change. So we're going to use the average rate of change formula, f of b minus f of a over b minus a. U would be my a, u would be my b. So finding f of b is me finding f of 6. And that would be 3, 6 squared plus 1. 6 squared is 36. 3 times 36 is 108. 108 plus 1 is 109. So that's f of b. F of a is a lot friendlier. I'm just plugging in 1. So that's going to be 3 times 1 squared plus 1. 3 times 1 squared is 3 times 1, which is 3, plus 1 is 4. So when I plug this all in, I get f of b, which is 109, minus f of a, which is 4, over b, which is 6, minus a, which is 1. That becomes 105 over 5. And that's a big fat 21. And that's going to be my guy. Like and subscribe. The position of an object moving along a straight line is given to you by the function s of t equals 5t to the fourth minus 16t cubed plus 8t squared, where s is measured in meters and t is in seconds. Find the velocity function. Well, the velocity function involves me just taking the derivative of the position function, and that's it. Not plugging in anything, that's it. So the velocity function is going to be s prime of t equals power rule, power rule, power rule. So drop down that 4, 20t to the third, drop down that 3, 48t squared, drop down that 2, 16t, and that's my velocity function. No harm, no foul. Easy peasy lemon squeezy. B is what is the object's acceleration at t equals 2 seconds? Well, the acceleration function is you taking the derivative of the velocity function. And so I need to do that and then plug in 2. So s double prime of t is going to be power rule, power rule, power rule. Drop down the 3, 60t squared. Drop down the 2, 96 regular t. Get rid of the t, 16. Now I'm going to plug in 2 into that equation right there. So s double prime of 2 is going to equal 60 times 2 squared minus 96 times 2 plus 16, and we just have some ugly math. 60 times 4 minus, what is that, 192 plus 16. 240 minus 192 plus 16 is going to be 64. Now, do I have any units? Do I have any units? Seconds, meters. So this is going to be meters per second squared. Okay, velocity would be meters per second. I didn't have to do that. But now I have meters per second squared. Okay? Now, the third question is going to be the grossest one of the three. At what time does the object change direction? Okay, now direction changes when velocity either goes from positive to negative or negative to positive. Okay, positive velocity in this case means you're going to the right. Negative velocity means you're going to the left. So if you were to go from right to left, that means you just changed direction. So I care about what we did in problem A and finding out where that happens. Now that's going to happen at a critical point. Okay, and in this case we might have 2 critical points, maybe even 3. So we need to find those critical points. So problem C involves me taking the velocity function and setting it equal to 0. So 0 is equal to 3t cubed minus 48t squared plus 16t. I have a 4 and a t in common with all of those, so let's rip that out. 4t, that's going to leave me with 5t squared minus 12t plus 4. So let's see if I can figure that out. So I'm going to have a 5t and a regular t. Those are my options. And positive 4 is going to be minus and minus. 2 and 2? Yep, that'll do it. So I have my 3 possibilities. And I'm going to be careful here, but all of them are going to work. 0 is going to be my first one. Okay. This one I'm going to set equal to 0, so 5t minus 2 equals 0. So if you add 2, you get that, and if you divide 5, you get that. And then t equals 2 is my other option. So I have 3 spots where at the very beginning, technically, you do have a direction change, so that kind of, I don't feel right saying at the beginning, but I'm going to say it anyway because it's a possibility, it's an option. Okay, it changes direction at 0, so I guess technically you're fine. But my seconds are going to be 0, 2/5, and 2 seconds. Of course, that's not in order, but who cares? Now, what you have to be careful of is what if any of these were negative? Well, if any of them are negative, then that's not an option because you can't have negative time. But yeah, that's what we're going to get here. So fun stuff. The position of an object moving along a horizontal line is given by s of t equals a third t cubed minus 3t squared plus 8t. Find all intervals where the object is speeding up. Now, the object speeding up means acceleration is positive. So I have the position function. The first derivative gives me the velocity. The second derivative is going to give me acceleration. So I need to go down to the second derivative here before I can do much anything. So let's take the first derivative. Okay, s prime of t is going to have power rule, power rule, power rule. So drop down the 3. A third of 3 is nothing. Well, 1, sorry. And that leaves me with t squared. Okay, drop down to 2, minus 6t. Get rid of the t, plus 8. That's the first derivative. That's velocity. That's not what I want. Second derivative is going to be 2t minus 6, nothing else. Okay, so I care about when this is speeding up. So what I need to do is I need to find my inflection points and make a sine graph. My inflection points are where the second derivative equals 0. So 0 equals 2t minus 6. This is where you're going to have a change from speeding up to slowing down and where you have 0 acceleration. Okay? So I'm going to add 6. 6 equals 2t. Divide 2, t equals 3. So if I'm making a sine graph of the acceleration function, I have an inflection point at 3. What I do in order to find where it's speeding up is I care when the acceleration is positive. So I take a point greater or less than 3. So if I pick 0 and pick 100, and plug it into the acceleration function, this will allow me to find out where this is negative and where this is positive. So if I take 0 and plug it into the acceleration function, I get 0 minus 6, which is negative. That means I'm slowing down. That's not what I want. If I take 100 and plug that in, 2 times 100 is 200, 200 minus 6 is positive. So this is where I'm speeding up. Spup. So this is speeding up at time t is greater than 3. Do I not have a seconds? I don't know. It doesn't say anything. So at time t is greater than 3 is where I'm speeding up. Do I include 3? No, because at 3 it's 0, which means at 3 it's neither. Okay, so that's how you find where an object is speeding up. A ball is launched into the air from the ground with an initial velocity at 48 feet per second. The ball's height is given by the equation s of t equals negative 16t squared plus 48t feet per second. Find the velocity of the ball the instant it hits the ground. So first thing I need to do is find out when it hits the ground. Okay? So I'm going to take the position function and know that this has to do with height. I know this is a parabola that's going to look like this. Okay, I'm going to set this equal to 0 because that setting it equal to 0 means that I'm on the ground. Okay, my height is 0 and s of t represents the height here. So it hits the ground when s of t equals 0. That's my position function. So I have negative 16t squared plus 48t. Let's factor out negative 16 and t. So negative 16t. And that leaves us with t minus 3. Okay, so my two options for t is going to be 0 and positive 3. Now, one of these is where it's launched, and one of these is where it hits the ground. I'm no mathematician, but I know 0 is not going to be where it's launched. So this hits the ground at t equals 3 seconds. Cool. Am I done? No. Because I care about the ball's velocity, or is it a rocket? What, a ball. I care about its velocity the moment it hits the ground. So I need to take that position function right here and find the velocity function by taking the derivative. So s prime of t is going to equal the derivative of negative 16t squared, power rule is going to be negative 32t plus 48. Now I'm going to take that 3, because that's when it hits the ground, and plug it in. So negative 32 times 3 plus 48. Negative 32 times 3 is negative 96, plus 48 is going to be negative 48. Now so feet per second. Why negative? Because it's going down, and the moment it hits the ground is 48 seconds. And this kind of makes sense, because if you launch it at 48, you're expecting the speed that it goes up to come down and hit the same speed the moment it hits the ground again. So the math seems to work out. Now, I know in the real world we have friction and stuff like that, and so that might take a factor, but not here, not in this make-believe problem that I created using ChatGPT. So there you have it. It's a lot of 4.2 stuff that we did. I hope you watched it all. And if you don't, go back and watch it all, like and subscribe. It began snowing at 6 a.m. The thickness of the snow in my yard, measured in centimeters, is modeled by that function s of t equals 10t plus 17. It's going to be a lot of snow. T represents the number of hours since 6 a.m. So we're talking about like already who cares? What is the derivative s prime of t? And what does it represent in this context? Well, the derivative is going to be you using the power rule. So s prime of t is going to be the derivative of 10t, which is just 10, and then nothing. So basically, what does it mean in this context? Well, basically that 10, if you take the derivative of something, you get a rate. Since my rate has to do with two units, one being centimeters and one being time in hours since 6 a.m., you're looking at getting 10 centimeters of snow per hour. Holy crap. Wow. Well, all right. So that's basically what you're getting at. The rate of change of the snow thickness per hour. That's a lot of snow. Of course, not realistic here, but yeah, that's what it gets. And this kind of makes sense too, because if you look at this guy, it reminds me of like slope-intercept form. 10 would be your slope. So like, your slope is a rate of change. So it works out both ways. Also, the word thickness makes me very uncomfortable. Thanks for watching. Like and subscribe. A function p of x equals 2x squared plus 12x plus 16 models the number of people standing in a line at a movie premiere, where the input variable x represents the number of hours since midnight. What is p prime of 8, and what does it represent in this context? Well, let's first off find out what p prime of x is. Okay, p of x is just a polynomial, so we're looking at power rule, power rule, power rule. All right, so the derivative of 2x squared is 4x. The derivative of 12x is 12, and then 16 becomes 0. Now, p prime of 8 is going to be 4 times 8 plus 12. 4 times 8 is 32, and 32 plus 12 is going to be 44. Now, what does this mean? Well, so we found out p prime of 8 is 44, so part 1 is done. Now what we need to find out is what it means in this context. Well, 8 would represent 8 hours after midnight. So we could say at 8 a.m., the derivative being 44 means the rate of change, because that's what derivative gives us, the rate of change is going to be 44 people per hour. Okay, so you're given a rate of change, and at this time, 44 people per hour are watching this movie at 8 a.m., so at that specific time. So that's what it means in this context. Fun stuff. As you ride on a moving Ferris wheel, your height above the ground in feet is given by the function h of t equals 50 sine t over 2 plus 60. T is measured in minutes. What is the instantaneous rate of change at your height after 6 minutes? All right, so h prime of t, I knew that. What does it represent in this context? Well, what I need to do is I need to take the derivative of h of t and see what that means here. So this is going to be chain rule. This part right here is chain rule. Okay, 50 stays there. Take the derivative of the outside, which is the derivative of sine, and you get cosine. Keep the inside t over 2. Now, I'm going to pretend that t over 2 is the same thing as half of t, so that when I take the derivative of the inside, I just view it as 1/2 of t, which makes the t go away, and I multiply everything by a half. Now, I'm not done taking the derivative yet, because the derivative of plus 60 is nothing. So, h prime of t is 50 times a half, which is 25, cos t over 2. Now, finding h prime of 6 means I'm going to have 25 cos 6 over 2, which simplifies to 25 cos 3. Now, really, this should have been a calculator problem, and I didn't include a calculator here. Maybe when I created this, I should have included a pi. That would make life a lot easier. But this is just going to be some number, and I have no idea what that number is, okay? But whatever that number is, what it represents is the fact that we are finding a rate at 6 minutes. Now, I have feet and I have minutes. My rate, what this means, is going to be whatever 25 cos 3 is minutes per, feet. I knew that was backwards. Feet per minute. So if I were to throw that in a calculator and find out what that is, that's what I would get. Okay? So when you take the derivative, you're finding a rate, and in this case, the rate is 25 cos 3 feet per minute, whatever 25 cos 3 feet per minute is. The graph of f of x is shown below. What is the value of f of 1 plus f prime of 1 plus 2f prime of 4? All right, f of 1 is going to be, what do I get when I plug in 1? I get 2, so f of 1 is 2, easy peasy. F prime of 1 is what is the slope at 1? Well, the slope at that moment is attached to this straight line here, where it's going to be a slope of positive rise 2, run 1, 2, so my slope is 1, so f prime of 1 is 1. F prime of 4 is asking what is my slope at 4. So I'm going to avoid using red. I almost did. So here's 4, right? It's attached to this line right here between that guy and that guy. So I care about the slope of this green line that I'm trying to draw out right there. This is a negative slope, so down 1, 2, 3, 4, 5, 6 over 1, 2, 3, 4. So f prime of 4 is going to be negative 6 over 4 is negative 3 over 2. So when I put this all together, I want 2 plus 1 plus 2 times negative 3 over 2. 2 plus 1, these guys cancel out, minus 3. It's going to be a big fat 0. So a very bizarre problem, but again, the point of it is to make sure you understand what derivatives look like on a graph, and can you also do some regular PEMDAS while you're at it? And we can. As a cat walks away from streetlight, the length of its shadow can be modeled by the equation L equals 3x, where L is the length of the shadow in feet and x is the distance from the streetlight in feet. Which of the following expressions shows this formula correctly differentiated with respect to time t? Now this is the introduction to related rates. We're going to write out our formula L equals 3x, and then we're going to differentiate both sides with respect to t. So we're going to ddt both sides. When you take the derivative of L with respect to t, the derivative of L is just a 1. But since we're taking the derivative of L with respect to t, we attach dl dt. On the right side, we're going to do the same thing. The derivative of 3x is 3. But since we're taking the derivative of x with respect to t, we're going to attach dx dt. So that 1 doesn't need to be there. And you have dl dt is going to equal 3 dx dt, which is going to be A. A spherical balloon is expanding, and its volume is modeled by the formula V equals 4/3 pi r cubed, where V is the volume in cubic inches and r is the radius in inches. Which expression can be used to find the rate at which the radius r of the balloon is increasing with respect to time t? So let's write out our formula. V equals 4/3 pi r cubed. What I want to do is I want to differentiate both sides with respect to t. So we're going to ddt both sides. Now the derivative with respect to t of v is just 1, but since we're taking the derivative of v, we attach dv dt like so. Now this is a coefficient, this is a coefficient, so we're going to focus on r cubed. So 4/3 comes along for the ride, pi comes along for the ride. The derivative of r cubed is going to be 3r squared. But since we're taking the derivative with respect to t, we are going to have dr dt attached. So the nice thing about this guy is the 3's are going to cancel out. The 1 doesn't really need to be there. And you have dv dt equals 4 pi r squared dr dt. Now they want us to use an equation that's solved for dr dt. So I'm going to divide both sides by 4 pi r squared. I'm going to put a 1 here, 4 pi r squared, even though I erased a 1 just a second ago. And I'm going to rewrite it like this. Okay, let me get a different color. Dr dt is going to equal 1 over 4 pi r squared dv dt. And that's the formula that we can use for dr dt. Fun stuff, related rates. If f of t is a continuous and twice differentiable function that represents the height of a tree in feet at any time t in years, which statement best describes the meaning of f double prime of 3 equals 4? All right, so f of t is the height of the tree. I don't know what formula it is, doesn't really matter. Now, f prime of t is going to be the rate of change. And that's going to be in feet per years. So if I were to do something and plug in 5, right, and get a number 12, that means it's growing at 12 feet per year. Great. I don't care about that. I care about f double prime of t. Now that is the acceleration, okay? And that's measured in feet per years squared, right? So that's how your rate of change is increasing or decreasing. All right, so what this means is that if I were to plug in 3 to get 4, f double prime of 3 to get 4 means that I am growing at 4 feet per year squared. Okay, so let's see what our options are. At time t equals 3, the tree's height is increasing at a constant rate of 4 feet per year. No, there's nothing constant about that. That's not true. That's talking about f prime of t, not what I want. At t equals 3 years, the tree's height is decreasing. Nope, because it's positive. That's not even an option. At t equals 3 years, the tree's height is increasing, which is true, and the growth rate is accelerating, at a rate of 4 feet per year squared. That's going to be my guy. The other option is at t equals 3 years, the tree's height is constant. That's not true. That's not true at all. Not true at all. Okay, so we have acceleration, and so C is going to be our acceleration. Nice. A cylindrical water tank has a radius of 3 feet. Water is being poured into the tank at a rate of 5 cubic feet per minute. What is the rate at which the water level in the tank is rising when the water is 4 feet deep? All right, so what we're dealing with is a cylindrical water tank. So we're dealing with volume equals pi r squared h. But we know that the radius is 3 feet. So the volume is pi 3 squared h. Okay, so I can write out 9 pi h. Now, this is a related rates problem because I'm asking you the rate at which the water level in the tank is rising. So what I want to find is dh dt, and I know that I am pouring water in at a rate of 5 cubic feet per minute. So I know that the volume is increasing, dv dt is equal to 5. All right, so let's plug in what we know. Well, first off, I can't even do that. Since this is related rates, I have to ddt both sides. So let's ddt both sides. The derivative of v with respect to t is dv dt. 9 is 9, pi is pi. The derivative of h with respect to t is dh dt, so 9 pi dh dt. Okay, I need to find dh dt. I know that dv dt is going to be 5, and that's going to be equal to 9 pi dh dt. Let's divide both sides by 9 pi, like that. And dh dt is going to equal 5 over 9 pi. Now you might be thinking, well, what about the 4 feet part? What about the 4 feet part? It doesn't matter. If you're pouring water in a cylindrical tank, it's not going to speed up if it's at 4 feet or 3 feet or 6 feet or whatever. Okay, it doesn't really matter. So that's how you do it. A 10-foot ladder is leaning against a wall. The base of the ladder is sliding away from the wall at a rate of 1 foot per second. How fast is the top of the ladder sliding down the wall when the base is 6 feet away from the wall? So, this is what we know right now at this very moment. We know that you're a ladder and you're 10 feet tall. Okay, don't know why I made my L look like that. So let's just get rid of it and pretend it never happened. My L is going to be 10 feet tall. I'll call you my H and I'll call you my B. What I have here is Pythagorean theorem. Okay, so I'm going to write out H squared plus B squared equals 10 squared, also known as 100. Now, what I need to do is I need to use related rates and ddt both sides. So I'm going to take the derivative with respect to t of both sides. All right, because this is mentioning my ladder sliding away from the wall at a rate of 1 foot per second, and I care about the speed at the top of the ladder sliding down. So that would be, I'm looking for dh dt, and I know what db dt is. So let's take the derivative of everything. The derivative of h squared with respect to t is 2h dh dt. The derivative of b squared is very similar, 2b db dt. The derivative of 100 is 0. That's nice. So let's see what I also know, because I seem to be missing a little bit of information. I know at this very moment, I care about the fact that the base is 6 feet away from the wall, so b is 6. I also know that if I use Pythagorean theorem, I can write out h squared plus 6 squared equals 10 squared, find out that that's going to be 36 equals 100, subtract 36, subtract 36, h squared is going to equal 64, square root everything, and now we're not going to include a plus or minus, and find out that h is 8. I could have also used the fact that this is a 3, 4, 5 right triangle doubled, but nah. So h is 8, so 2 times h. dh dt is going to be the speed at which the height is changing, and that's what I'm looking for. So dh dt, no changes there, plus 2 times b is 6, nope, yep, 6 at the moment, and db dt is 1 because that's how fast it's sliding away. That's going to equal 0. So 16 dh dt plus 12 equals 0. Subtract 12, 16 dh dt equals negative 12. Divide by 16, divide by 16, and you get dh dt equals negative 3/4. Now my unit of measure is feet per second, so we'll say feet per second. And there you have it. That's the ladder problem. Fun, fun, fun. The radius of a circle is increasing at a rate of 3 inches per minute. What is the rate of change of the area of the circle when the radius is 4 inches? All right, so let's write out our formula for the area of a circle. A equals pi r squared. I care about the change in the area, so I'm going to dA or d dt both sides. So d dt, d dt. The derivative of a with respect to t is going to be dA dt, and that's going to equal, nothing happens here with pi, multiply by 2, make you an r, and attach dr dt. Okay, whenever you take the derivative of an r squared with respect to t, you have to attach the derivative with respect to t. So, what do I know? I know that what is the rate of change of the area when the radius is 4 inches, but also the radius of the circle is changing at 3 inches per minute. All right, so the radius is 4, so dA dt is going to equal pi times 2, the radius is 4, and dr dt is 3. So that simplifies out to 2 times 4, which is 8 times 3, which is 24. 24 pi inches per minute. And that's how you do it, related rates. Let f of x equals x squared plus 2x. Find the linearization L of x of the function at the point a equals 1. Well, the linearization formula is this. L of x equals f of a plus f prime of a times x minus a. If you're looking at that and thinking point slope thoughts, you're thinking correctly. Okay, but let's write out what we know. We know that f of a is going to be f of 1. So we'll say this, f of a equals f of 1. F of 1 is going to be 1 squared plus 2 times 1, which is going to be 3. All right, in order to find f prime of a, or f prime of 1, I have to find f prime of x, which is 2x plus 2 using power rule. So f prime of a is going to be f prime of 1, which is going to be 2 times 1 plus 2, which is 4. Also, a is 1. I can handle that. So writing out my formula, the linearization is going to be L of x equals f of a, which is f of 1, which is 3, plus f prime of a, which is f prime of 1, which is 4, times the quantity x minus a, x minus 1. And that's how you do it. For the function f of x equals e to the x, find the equation of the tangent line at x equals 0. Now, we have all this information from Unit 1, maybe Unit 2, how to do this, but this is the linearization section, so we're going to use the linearization information that we can come up with. So L of x is going to equal f of a plus f prime of a times the quantity x minus a. Now, when it says x equals 0, that's you basically saying a equals 0. It's the same exact thing. So let's find out what we can find out. F of a means f of 0. F of 0 is e to the 0, which is 1. F prime of x is going to get me my f prime of a. The derivative of e to the x is e to the x. So f prime of a is f prime of 0, which is e to the 0, which is 1 again. And since I'm calling a equals 0, I now have enough information that I can do this problem. All right, so they're calling L of x y, so let's call L of x y. F of a is going to be 1, plus f prime of a is going to be 1. X is x, minus is minus, a is 0. So y equals 1 plus 1 times x, which is y equals 1 plus x. So u. So again, we could have done this stuff using our old traditional methods, but they want us to use linearization here because linearization looks an awful lot like point-slope form. It's very, 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 very similar. In fact, it's almost the same exact thing, just with more derivatives and stuff, and so this method works just fine. Given the function f of x equals ln of x, approximate f of 3 using the tangent line at a equals 3. Well, we're going to do this using the linearization method. The linearization method says L of x equals f of a plus f prime of a times x minus a. All right, so let's see what we can find out. F of a is going to be f of 3. And this should have been a calculator section, but f prime of 3 is going to be 1.0986, which is why I pointed over here. I did that ahead of time. Doesn't mean anything, but it might mean something. I mean, the numbers, looking at the numbers ahead of time, I have a weird feeling about this. F prime of x is going to be the derivative of ln of x, so 1 over x, which means f prime of a is going to be f prime of 3, which is going to be 1 over 3. A is 3, and now we have all the information that we need. So L of x is going to equal f of a, which was that gross number, 1.0986, plus f prime of a, which is 1/3, times, now they want us to find f of 3, which means x is 3. So 3 minus a, which is 3. So that is going to become 0, and a third times 0 is that, which means L of x is going to be that. So kind of a bizarre problem, but that's what we end up with. So that's how you can do it. Good old L'Hopital's rule. Now, L'Hopital's rule is going to help us when we try to plug in our number. And if we get 0 over 0 or infinity over infinity, we have problems. Now, most of us would look at this and think of Unit 1 and be like, well, let's just factor this out. Well, L'Hopital's rule gives us a different option. L'Hopital's rule says that if I were to plug in 2, I would get 2 squared minus 2 squared, which is 4. That would be 0. I would get 2, that would be 0. That is an indeterminate function. Okay, that's bad. All right, so I can't plug in 2. Now, I'm not going to factor, because L'Hopital's rule says that I can just take the derivative of the top So the limit as x approaches 2, let's take the derivative of the top, d dx, the top, so x squared minus 4, and the derivative of the bottom, so d dx, x minus 2, and then repeat the process. Okay, so the limit as x approaches 2, the derivative of x squared minus 4 is 2x, and the derivative of x minus 2 is just 1. So now I can plug in 2, and I can get 2 times 2 over 1, which is 4 over 1, which is 4. So L'Hopital's rule says we don't need to factor anymore. We'll just take the derivative of the top, the derivative of the bottom, try it again, see what happens, and if it works, it works, and it did. If it doesn't work, repeat. But in this case, it worked. Everyone wins. Compute the following limit. The limit as x approaches 1 of x squared minus 1 over ln of x. Well, if I were to plug in 1, I'd get 0 up here, and if I were to plug in 1, I'd get 0 down here. That's indeterminate. That's against the rules. So we have a little guy called L'Hopital's rule that we can use if we can't factor anything out and make anything disappear. L'Hopital's rule says that I can take the derivative of the top, so the d dx of x squared minus 1, I could take the derivative of the bottom, so d dx of ln of x, and try it again. So the derivative of x squared minus 1 is 2x. So I'm taking the limit as x approaches 1 of 2x, and the derivative of ln of x is 1 over x. I can plug in 1 now. So when I do, I get 2 times 1 over 1 over 1, which is 2 over 1, which is 2. So L'Hopital's rule helps me out if I get 0 over 0 or infinity over infinity, but 0 over 0 is what I got. Since I can't factor, L'Hopital's rule is the only option I can take. Calculate the limit as x approaches 0 of sine 3x over x. Now, if I were to plug in 0, I would get sine of 3 times 0, which is the sine of 0, which is 0. 0 on the bottom means that this is indeterminate. Okay, so I can't do this. Now, I can't factor anything else either, which means I have to use L'Hopital's rule. So L'Hopital's rule says this. If I take the derivative of the top, so if I d dx sine 3x, and if I d dx x, I should be able to do that, plug it in again, and see if it works. So the derivative of sine 3x requires the chain rule. All right, so I'm going to take the derivative using the chain rule. So let me just write out my limit again. Take the derivative of the outside, which is cosine. Keep the inside, which is 3x, but then multiply everything by the derivative of the inside, which is 3. So I have 3 cos 3x. And now we take the derivative of over x, which is 1. That's nice. So I can plug in 0 now. If I take the derivative, if I plug in 0, I get 3 cos 3 times 0 over 1. Over 1, useless. 3 cos 0 is the same as 3 cos 1 because the cosine of 0 is 1. And last time I checked, 3 times 1 is a big fat 3, which means B is going to be my answer, baby. So L'Hopital's rule is used if you take your limit, get 0 over 0, or infinity over infinity. You take the derivative of the top, take the derivative of the bottom, try again, repeat if necessary. No need. I got my 3. I'm done. Evaluate the limit as x approaches 0 of 2x over sine 6x. Well, if I plug in 0 in the top, I get 2 times 0, which is 0, no good. If I plug it in on the bottom, I get sine of 6 times 0, which is sine of 0, which is 0. That's indeterminate. That's also no good. So I'm going to use L'Hopital's rule. And L'Hopital's rule says that I can take the derivative of the top, so the d dx of 2x, the derivative of the numerator, and take the derivative of the denominator and try it again. Okay, so let's do just that. All right, the derivative of 2x is just 2. So I'm going to find the limit as x approaches 0 of 2. If I take the derivative of the denominator, okay, that's going to be taking the, now this is chain rule, so take the derivative of the outside, which is cosine, keep the inside, which is 6x, but multiply everything by the derivative of the inside. The derivative of 6x is just 6. Okay. Now I should be able to plug in 0. So 2 over 6 cosine 6 times 0 is going to be 2 over 6 times cosine 0. Cosine of 0 is 1, so we're in good shape. 6 times 1 is going to be 2 over 6, which is going to be 1/3. Okay, so L'Hopital's rule is used if you get an indeterminate function, which is 0 over 0 or infinity over infinity. Take the derivative of the numerator, take the derivative of the denominator, try it again, see if you get a number. We did. Everybody's happy. Calculate the limit as x approaches infinity of e to the x over x squared. Now, if you remember a lot of your pre-calculus rules or maybe even your early calculus rules, you know that this is going to go towards infinity because you grow at an exponential rate higher than that. But this is the L'Hopital section, so we're going to use L'Hopital's rule. L'Hopital's rule says that if I were to take the derivative of the numerator and the derivative of the denominator, I can try it again. Now, originally we get infinity over infinity. That's bad news. If I plug in infinity in air quotes, I get infinity over infinity. So let's take the derivative of the numerator. The derivative of e to the x, last time I checked, is e to the x. The derivative of x squared is 2x. If we plug infinity in, we get infinity over infinity again. No big deal. You can use L'Hopital's rule as many times until you get a number or what it is that you're looking for. So if I take the derivative of the numerator and the denominator again, I get e squared over 2. Now, if I plug in infinity, I get e to the infinity over 2, which is a huge number, over 2, which is just infinity. Again, we know this because we know that you are going to grow so much faster than you. The magnitude at which e to the x grows is going to be so much more than x squared because it's an exponential function versus a quadratic function. But we did L'Hopital's rule anyway, and boy did we have fun. Evaluate the limit as x approaches 0 of x squared over cotangent x. Now this is L'Hopital's rules section, so we're going to use L'Hopital's rule. And the reason why is if you were to plug in 0 into cotangent of x, you get something that's undefined. Why is that? Well, let's rewrite this out in 3 separate parts, because I'm allowed to do this. Okay, I'm going to write this out as x squared times whatever cotangent is, which is going to be cosine x over sine x. Now my issue right now is if I were to plug in 0 in for sine x, I would get 0. That's no good. So since this is a limit, I'm allowed to rip this apart any way I want. And so the way I'm going to rip this apart is I'm going to say the limit as x approaches 0, I'm going to rip apart sine and cosine and make it its own guy. I'm allowed to do that. I'm going to keep an x there and an x up here. I'm allowed to do that too. And now we take each limit separately. Okay, so I'm allowed to plug in 0. That's all good. Now, I can't plug in 0 yet, but if I take L'Hopital's rule, I'm going to take the limit as x approaches 0 of me taking the derivative of the numerator and me taking the derivative of the denominator. Now we're in good shape because I can plug in 0 into cosine and I'm in good shape. Okay, the derivative of me plugging in 0 to cosine 0 is going to be cosine 0, which I'll fix that in a minute. Okay. Now you're still 0, which means everything is just basically going to be destroyed anyway. But if I were to plug in 0, I would get 1 over cos 0, and cos 0 happens to be 1. So you become 1 over 1, which is 1, times 1, and 0 times 1 is 0. So after all of that, we get 0. But we used L'Hopital's rule and a little bit of fun math to rip everything apart. And we ended up with a nice answer anyway, and that nice answer is 0 en español. End Unit 4.